So today I want to talk about the areas and perimeters of rectangles and squares. And we're going to use a little bit of geometry for this and also some of the work that we did on equations in some previous videos. So let's start with a little bit of motivation. Let's look at a 5 by 5 square. You can imagine like the scenarios which are described in many math textbooks. You're given some length of fence, maybe you're given 20 meters of fence, so you've got a perimeter of 20 meters to work with. You arrange it into a square, and that sections off an area, this inside section here, which has area 25 meters squared. And by contrast, we could have taken that same 20 meters of fencing and sectioned off a different area, a different rectangular area. For example, we could have done a 3 by 7 meter area, in which case the perimeter remains 20 meters, right? 3 plus 7 plus 3 plus 7. But now the area is 3 times 7, which is 21 meters squared. So we see that in this example, switching from a square area to a rectangular area has resulted in a decrease to the total amount of area captured, even though the perimeter stayed constant. So even though we used the same amount of fence, we got less area when we did it in a rectangle rather than a square. And the question that we might ask is that always the case? Does a square maximize the area among rectangles of a fixed perimeter? So this is just a way of expressing the question. If you fix the perimeter and you fix the fact that you have to make it into some type of rectangle, with a square being a special case of a rectangle, is a square the best shape you can do in terms of capturing the most area? Okay, and the answer to this question is yes, and the way to prove it is by, there's several ways of proving it, but let's kind of explore what happens if we let x and y stand for the side lengths of the rectangle that we're constructing, and we have total perimeter 2x plus 2y equals p. So instead of making the perimeter some specific number like 20, I'm just going to say the perimeter is p, so this is a general proof. And I'm going to write 2x plus 2y equals p. This is the equation that captures the fact that no matter what x and y are, they have to add up to our perimeter of p. Now it's going to be convenient for me actually to draw this by sectioning off this amount d here, which is the amount that y is more than x. So in the special case where d is equal to 0, that means that y equals x and we have a square. Otherwise, I'm letting x stand for the smaller side and x plus d stand for the larger side. And of course, in this case, what we have is that our total perimeter p is equal to 2x plus 2y, which you can check is 4x plus 2d. Okay, because I can express y in terms of x and d. This just helps me think about what's going on geometrically, and it sort of focuses the attention on this variable d here, which tells me how much longer is the longer side than the shorter side. And we're going to show that it's when d is equal to 0, which that's when you get the highest area. So what is the area? Well, the area, of course, is x times y, which is equal to x times x plus d, because y is equal to y is equal to x plus d. And what's x plus d? What's x times x plus d? Well, I actually don't like this expression because it has two variables in it, the length of the short side and this d, which is the length that you have to add to get the longer side. And two variables is hard. I want one variable. And that's where this is going to come in. This here is a constraint. It tells me that there's actually a relationship between x and d. They're not just two arbitrarily chosen variables. They have to add up, when you add them up in this way, to the fixed perimeter, right? So what is it that we have exactly? I'm going to come and use some space over here to make it a little bit clearer. We can solve this equation for x. So we can get that 4x equals p minus 2d, which implies that x equals p minus 2d over 4. So if that's what x equals, then I can also solve for x plus d. That equals p minus 2d over 4 plus d. That equals p minus 2d over 4 plus 4d over 4, common denominator. And that equals p plus 2d over 4. So let's put this together. We have an expression for x. We have an expression for x plus d. And we know that the area is the product of those two things. So the area is equal to p minus 2d over 4, that's x, times p plus 2d over 4, that's x plus d, which is equal to p squared plus 2pd minus 2pd, so those cancel, minus 4d squared over 16. And this is an extremely useful expression of the area for our purposes, because what it shows us is that the area of the figure is determined by taking the perimeter squared, subtracting this amount, which is 4 times the difference d squared, and dividing by 16. Now you can check that, for example, when p equals 20 and d equals 0, then we're in the 5 by 5 square case, and that implies that the area is equal to 25. You can plug those numbers into this formula to check that it works out. And similarly, when p equals 20 and when d equals 4, which corresponds to our 3 by 7 rectangle, because the difference there between 3 and 7 is 4, that gives us an area of 21, as we expect, just by plugging into this formula. But the really important part of this formula is that it's done for an arbitrary perimeter and an arbitrary difference d between the short side and the long side. And what we see is that that difference d, if the entire effect that it has on the area is a subtracting effect. Whatever d is, when you square it, you get something which is positive if d is positive. This is only 0 if d is 0. So whatever d is, if it's positive, it's making the area smaller. You can see it right here from the subtraction. So the answer to this question is yes. Whenever d is a positive number, it makes the area smaller, which means that the area is largest when d is equal to 0, which is when you have a square.